Hello class, welcome back. In this video we begin chapter 4. Now to me, this is where the fun really begins. Well, kind of. I do think that probability is a much more interesting chapter than some of the other ones in this course. Of course, the other ones are very exciting in their own ways, but probability I think is the most interesting. So we are going to talk about the basic concepts of probability. So the most important objective of this section is to interpret probability values. Probability is always going to be between 0 and 1. You can't have a probability greater than 100% or a negative probability. So a probability of 0 would be an impossible event, and a probability of 1 being it's guaranteed to occur. Then we'll talk about odds in the context of maybe gambling or the lottery or what are the chances of this happening? We're talking about that kind of probability. Okay, so common probabilities, just to kind of get the context and the terminology going forward. So you flip a coin. The likelihood of flipping a heads is 1/2 or 50%. If you roll a dice, there are 6 sides, and each one has an equal probability of it landing. So it's a 1 in 6 chance or 16.66% chance that it'll be any individual number. So the basics of probability. An event is any collection of results or outcomes of a procedure. So don't overthink this. Flipping a coin is an event. Picking a name out of a hat is an event. It's just the occurrence. Rolling a dice is an event. Picking a card from a deck is an event. It's just any time that you are conducting something where a probability will be occurring. A simple event is an outcome or an event that cannot be further broken down into simpler components. So when rolling a single dice, the outcome of 5 is a simple event, but the outcome of an even number is not a simple, because an even number could be a 2, 4, or a 6, so an even number could be broken down further. But rolling a 5, well, you can't break a 5 down any further. That would be a simple event. With one birth, the result of one girl is a simple event, and the result of one boy, another simple event. They are individual simple events, cannot be broken down any further. With 3 births, the result of 2 girls followed by a boy is a simple event, because you can't reduce that any further. However, with 3 births, the event of 2 girls and 1 boy is not a simple event, because it can be broken down further. 2 girls and 1 boy, the birth order could be girl, girl, boy, girl, boy, girl, boy, girl, girl. These are 3 simple events, but the statement 2 girls and 1 boy with 3 births is not simple. So hopefully that makes sense as we move on. So the sample space is the next term that we need to discuss. The sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. So the sample space is just the accumulation of all the simple events. So for a single birth, the event is 1 girl. There's no other possible outcome. And then the sample space consists of all possible simple events. Whereas 3 births, you can have all these different outcomes. That would be your sample space. Okay, so the basics of probability. So say a couple has 3 children. Okay, let's call this our first child. First child could be a male or a female. The second child, male or female. Third child, male or female. But now if you want to look at the outcomes of all 3 births, well, here are your possible events. And you've probably done these before where you kind of make these tree and branches. So now it could be male, 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 female, male, female, male, and so on and so forth. So you look at this last one right here. This tells you all the possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 possible outcomes. One outcome is male, 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 one is female, 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 and the rest are a combination of 2 and 1. So now some notation for probabilities. Now this section does have a lot of basic terminology and notation that we have to get through to move forward. So P of X is just the probability of event X occurring. So if we say the event is rolling a 6 on a die, so P of X would be the probability of rolling a 6. P of X is equal to X over N, where X is the number of times X happened divided by the total number of times you tried. So if you roll the dice 6 times and you got 4, for example, that would be 1 success over 6 attempts. Probability is 1/6. So some examples are probability of drawing an ace from a deck of 52 cards would be 1 in 13 when you reduce 4 over 52 to its simplest form. So range is a probability. We talked about this a little bit before. So probability can be expressed as a decimal, fraction, or percentage. The values must be between 0 and 1. It cannot be greater than 1 or a negative value. So probability of 0 would be could never, ever, ever occur. Probability of 1 is it's guaranteed to occur. So all probabilities must be between 0 and 1. Obviously, a 0.5 would be a 50-50 chance. Think of having a boy or a girl, or getting a heads or a tails. Okay, so 3 common approaches to finding the probability of an event. Number 1, relative frequency approximation of probability. So you are conducting or observing a procedure and then counting the number of times something occurs. So then it would be the probability is the number of times it occurred divided by the number of times the procedure is repeated. So you're just looking at it from empirical data. Example, you're working at McDonald's and then you have, 30 customers walk in, 4 of which order a Big Mac. So you would say, okay, the probability of a customer ordering a Big Mac would be 4 divided by 30. The classical approach to probability is requires equally likely outcomes. So if a procedure has n different simple events that are equally likely, then you can determine P of A by saying the number of ways that A can occur divided by the total number of simple events. So this isn't looking at empirical data. This is just looking at what the probability is just based on the nature of whatever it is that you're conducting. So the probability of having exactly 2 boys in a family of 3 children, you know the probability of having a boy. Another one is rolling a dice again, or flipping a coin, or selecting a card from a deck. Those are all, you can calculate the probability just based on the nature of the sample space. Whereas this one, you're conducting kind of an experiment of sorts to get raw data. Okay, and then we have subjective probabilities, which is the probability of event A is estimated by using knowledge of the relevant circumstances. Okay, so then next is the law of large numbers. So as a procedure is repeated again and again, as the number of times you conduct it goes to infinity, the relative frequency probability of an event tends to approach the actual. And what we mean by that is, say you flip a coin 3 times. You know the odds of getting a heads are 50%. But if you only flip a coin 3 times, you're either going to get the probability of heads being 0 if you get no heads, 33% if you get 1 out of 3, 66% if you get 2 out of 3, or 100% if you get 3 out of 3 heads. However, we know that it should be near 50%, but none of these 4 possible outcomes give you a result of 50%. So does that mean that flipping a coin and getting a heads is not 50%? No, it just means that you need to conduct more and more experiments and flip that coin more and more. So as that coin gets flipped several more times, the recorded probability will approach the 50% or the actual probability. Let's look at an example. So find the probability of dying. Ooh, morbid. Find the probability of dying when making a skydiving jump. So this is actually a soft spot for me in my relationship, as my fiance thinks that skydiving is so dangerous and not worth the risk. Whereas I think it's the risk is worth the reward of having that memory and that video. So maybe we'll show her this example right after to show that, hey, the chances of it actually leading to death are pretty low. So in a recent year, there were about 3 million skydiving jumps, and 21 of them resulted in deaths. We will use the relatively frequency approach as follows. So the probability of dying is the number of people who died divided by the number of people who jumped. So 21 over 3 million, 0.000007. Okay, so that's a very low percentage of people dying from skydiving. In a study of U.S. high school drivers, it was found that 3,785 texted while driving during the past 30 days, and 4,720 did not text while driving during that same time. Based on these results, if a high school driver is randomly selected, find the probability that he or she texted while driving during the previous 30 days. Okay? So we need to first figure out how many high school student drivers we have. So we have to add the number that texted while driving plus those that did not text while driving. So now we know we have 8,505 total number of drivers in the sample. We can now use the relative frequency approach to say, okay, we want to know how many what's the probability of randomly selecting someone who texted while driving. So we need to take the number of drivers who texted while driving divided by the total number of drivers in the sample. Thus, we get 3,785 divided by 8,505, so we get a 44.5% or 0.445 probability that if a high school driver is randomly selected, he or she texted while driving during the previous 30 days. Okay, the next is a complement. So the complement of event A, denoted by a hat with or a bar, with the A with the line over the top of it, consists of all outcomes in which event A does not occur. So it is the complement of A is a bar, and it's basically the opposite. So if the probability of event A is equal to the probability of flipping a heads, then the complement of that, P A bar, will be the probability of not flipping a heads, or in this case, flipping a tails. So it's just whatever outcomes do not include probability of A. So if probability of A is rolling a 2 on a fair dice, the probability of A bar would be the probability of not rolling a 2, or the probability of rolling a 1, a 3, a 4, a 5, and a 6. It's just pretty much the opposite. And then probabilities, and this irks me because they wrote complement, like you're giving someone a nice word of affirmation, but it's complement, but we'll roll with it. The probabilities of complementary events, so just some things to note. If two events are complements, if the probability of A plus the probability of B equals 1, the probabilities are also complements if the probability of getting event A and probability of event B is equal to 0. And to find the probability of a complement, you just have to do probability of the complement is equal to 1 minus the probability of the event. And these are pretty important formulas. So I'm going to spend a quick minute just talking through them via an example. So we would say that, let's look at this previous example. The probability of event A is the probability of flipping a heads. So the complement of that is not flipping a heads, or getting a tails in this case. We know that the probability of getting a heads is 50%. The probability of flipping a not heads or a tails is also 50%. 50% plus 50% equals 1. Two events are also complements if the probability of A and B occurring are equal to 0. Well, if you flip a dice, or a head, or a coin, what's the probability of getting a heads and a tails? Well, you're not going to get both. You can only get one or the other. So the probability of getting both heads and tails in a single flip of a coin, that's 0. Okay? And then to find the probability of a complement, you use this formula here. So let's say that you are choosing picking a card at random, and you want to know what is the probability of getting the ace of spades. Well, you know if there's only one ace of spades, so the probability of event A, which is ace of spades, would be 1 over 52. So what's the complement of that? Well, it would be the probability of not getting an ace of spades. So that would be 1 minus 1 over 52, which would give you 51 over 52, which makes sense because out of 52 total cards in a deck, 51 of them are not the ace of spades. So let's look at the complement of death from skydiving. So same example, but now we want to know what's the probability of not dying when making a skydiving jump. So among 3 million jumps, there were 21 deaths. So it follows that 2,999,979 jumps were survived. So to get that probability, we can do the 2,999,979 divided by the 3 million, which would give us that probability. Or we could have said let's go back a few slides. Let's see if I can find it. 1 minus this value will give us the probability of not death or surviving. So now we want to know what makes something have a significant result. So we say that X is significantly high if the number of successes has a probability less than or equal to 0.05. And the 0.05 isn't absolutely rigid. What we mean by that is a lot of times we want to know what's in the 5 percentile. That's the basis. But a lot of times we want to know the 99 percentile or the 98 percentile. But generally speaking, we want to know what's in that significant range. Remember in the previous chapter we talked about anything exceeding a magnitude greater than 2 standard deviations is significantly high. Well, that's the same concept here. We said that 95% of all data values fall within 2 standard deviations, which means that for it to be significantly high, it needs to be in that last 5%. That's where that 0.05 number is coming from. Okay? Significantly low would just be the other end of that. Okay, so probability review summary. The probability of an event is a fraction or decimal between 0 and 1. Impossible event is 0. Guaranteed to occur is 1. And then we talked about the probability of event A is shown as this P of A. And then P of A bar would be the probability that event A does not occur. And that's the complement. Okay. Next, we will talk about odds. And you know odds if you've ever been to a casino or played the lottery. So actual odds against. The actual odds against event A occurring are the ratio P of the complement of A divided by the P of A, usually expressed in the form AB, or A to B, where A and B are integers. Reducing the largest common factor, if A equals 16 and B is 4, you would say the odds against are 4 to 1. Instead of 16 to 4. Just kind of a way that we use the terminology. Same concept if you've ever been to like a horse betting track or anything like that. So this is the ratio of losing to winning, and then it's expressed as these odds. So if you're playing roulette and bet black, the odds of losing, odds against, is the probability that a green or red is the result compared to the probability of a black being the result. So let's look at that example a little further. There are 38 positions along the wheel where the ball can land in a game of roulette. You have 38 total little positions, 38 numbers. 18 of them are black, 18 are red, and then 2 are green. Casinos will pay you 1 to 1 if you select black or red and are correct. So if you bet on $5 on black and then they roll it and then the ball lands on a black one, you win 1 to 1. So they'll give you $10 back for a profit of $5. So of that $10 that you get back, 5 is your original bet, 5 is your profit. So the actual odds in favor of event A occurring are the ratio P of A divided by P of A bar, which is the reciprocal of the actual odds against. So if you're playing roulette and bet black, the odds of winning, odds in favor, is the probability that a black is the result compared to the probability of a green or red being the result. Which in roulette, if you bet on black, your odds of winning will be 18 divided by 20. So slightly less than a 50% chance of winning. That slightly less than 50% chance of winning is why the casinos make money. If it was exactly 50%, if there were actually no greens over here, then the odds of winning would be half, and the casinos wouldn't have any advantage. So casinos need to have these green sections in here just to create the odds ever so slightly in their favor. The payoff odds against event A occurring are the ratio of the net profit, if you win, to the amount bet. So the payoff odds against event A is the net profit to amount bet. So casinos will pay you 1-to-1 if you select black or green and are correct. So the payout would be net profit to amount bet, 1-to-1. If they paid you 2-to-1, then that would mean that you would get $15 back, 5 of which is your original bet, and then $10 is your net profit, compared to your 5, which is your original bet. But we wouldn't say 10-to-5, we would say 2-to-1. We would reduce that down to its simplest form. Okay, let's look at an example. Actual odds versus payoff odds. If you bet $5 on the number 13 in roulette, your probability of winning is 1 in 38. But the payoff odds are given by the casino are 35-to-1. So let's look at the wheel again. I'm betting on 13. So I'm saying, okay, I bet $5 that this next roll will land on this 13. There's a 1 in 38 chance on being correct. There's 38 numbers and only one will give me a win. So there's a 1 in 38 chance of being correct. And if I'm correct, then they'll pay me 35-to-1 odds. So we want to know, what are the actual odds against the outcome of 13? How much net profit will you make if you win by betting $5 on 13? If the casino was not operating for profit and the payoff odds were changed to match the actual odds against, how much would you win if the outcome were 13? Okay, so let's look at part A. Part A is find the actual odds against the outcome of 13. So with P of 13 equals 1 over 38, and the probability of P is not 13 would obviously be 37 over 38. We get the actual odds against being 37 over 38 divided by 1 over 38. The 38s cancel, so we get 37-to-1. There is a 37-to-1 odds that we will lose. Now notice how 37-to-1 odds that we will lose, but a payout for a victory is only a 35-to-1 odds. Again, that's why the casinos make money, because theoretically it would take me 38 rolls of the roulette ball to get a 13, so I would lose 37 times. But the one time I do win, I'm only getting 35-to-1 odds. So as the number of rolls goes to infinity, the casinos is making that difference. In an overly simplistic form, but yes. Okay, part B. What did part B say? How much net profit would you make if you win by betting $5 on 13? Okay, so the casino payout odds against 13 are 35-to-1. So 35-to-1 is the net profit relative to the amount bet. So there is a $35 profit for each $1 you bet. So for a $5 bet, $175 is the net profit. So 35 times 5, $175. So the winning bettor would collect $175 plus the original bet. So if I put $5 down and I win, the dealer would hand me $180 back. My original $5 plus the net profit of $175. Okay? C. If the casino were not operating for profit, the payout odds would be changed to 37 to 1, which are the actual odds against the outcome of 13. So with payout odds of 37 to 1, there is a net profit of $37 for each $1. So instead of doing 35 times 5, now I'm doing 37 times 5. So for a net profit of 185. However, obviously casinos are in it to make money, so the casino makes its profit by providing a profit of only $175 instead of the $185 that would be paid if the roulette game had a fair payout instead of favoring the casino. And that $10 difference, that is their margin. That's how they make their money. Okay, there was a lot of material in this section, so take it slowly. Make sure you look at all the homework, and best of luck. Any questions, always email me.